And at the heart of that idea is forces. In physics, we represent forces as vectors which have both magnitude and direction.
With both direction and magnitude. Oh yeah!
Okay, so usually a few different forces will act on an object, and we can represent those with what we call a free body diagram. So first, for an object in motion, let's say a box on some surface, you would assume that gravity would be holding it down, and then the force of the surface would then be holding it up. So then those two arrows are equal in distance to each other. But if it's in motion, maybe someone's exerting a force on it that's going towards the right. And then maybe there's just a little bit of drag on it coming back. For an object in equilibrium, it means that the arrows are going to be equal on all sides. So we can assume the same thing, the gravity and the surface pushing back up, but also we would assume that the force going forward and then maybe the drag would be equivalent, and then of course gravity and the surface.
Now on to Newton's laws of motion. According to Newton's first law of motion, objects at rest stay at rest, and objects in motion stay in motion unless acted upon by an unbalanced force. And now Newton's second law states that force is equal to mass times acceleration. Acceleration is the change in velocity.
For example, this individual was in motion, very evidently, until he was not.
For an object in a state of equilibrium, the net force is equal to 0 because the net force is equal to the mass times the acceleration, which is 0 in this case. Additionally, the sum of the forces in the x direction have to be balanced and also equal to 0, as well as the forces in the y direction.
Alright, so a moment is basically the turning effect around an axis or a pivot. So for example, we have a wrench tightening around a bolt, and so that turning motion is going to be measured by the force and the distance. So this is important because if there's no distance, so if the force has no turning effect on it and it stays fixed in the position it's in, there's not going to be a moment. So it requires a change in the distance and an applied force. And the force is also always perpendicular to the axis.
So we're going to be doing an example about solving a very, very simple mechanics problem. Our example is a mass is resting on a table. You and your friend are pushing on opposite ends of the mass. The mass is in equilibrium. This is a key part. What is the force you are applying? What is the force the table is applying? The mass here given is 14 kilograms, and gravity we're rounding up to 10 meters per second. So we're given this diagram of the forces that are currently happening in this problem. So step one is always to create a free body diagram. In a free body diagram, we just want to simplify it as much as possible. So this mass we can turn to a point. We see that there's F1 acting in this direction. F2, which is opposing it. We know there's gravity acting downwards. And normal force from the table acting upwards. So from here, we can set up our system of equations. Using Newton's laws, we know that the sum, when in equilibrium, we know that the sum of forces in x must be equal to 0, and the sum of forces in y as well. So we can set up a matrix to solve this equation. Set this up here. We see our forces in x. We have F2 acting in the positive direction and F1 acting in the negative. So we'll do positive F2, so our forces in x, negative F1. We have Ft acting upwards in the positive direction, and Fg and the negative, Ft and negative Fg, where we know that these are forces in x and y, so this is in x and this is in y, and because it's an equilibrium, it must be equal to 0. So from here, this is a very, very simplified problem, just to kind of get the concept down. But we see that for x, F2 minus F1 is equal to 0, and for y, F table minus F prime is equal to 0. We can then take this a step further and see that F2 is equal to F1, and the force on the table is equal to Fg. Then you can substitute your numbers in and get the numerical value, but this is the concept behind how to solve a system like this, and the very, very basics of solving mechanics problems. So now, using Newton's laws that the sum of forces in x and the sum of forces in y must be equal to 0 when we're in equilibrium. That's key. We can create these equations. So using trigonometry, we see, because this is 45 degrees, that the x components must be multiplied by root 2 over 2, and the y components as well. Because in a 45-degree angle, the component x is equal in magnitude to the component y, which is why we get the same value here. We see that t1 is positive in the positive x direction, and t2 is in the negative x direction, which is why we have a minus sign. And then it's equal to 0 because there's no other forces acting in y, and x, sorry. Then we get to forces in y. We see that T1 is acting in the positive x direction, which is why this is positive. T2 is also acting in the positive x direction. But then we have this additional gravitational force, mg, which is pulling down, so it's negative. It's equal to 0. This can then be solved, or can be rewritten as an equation in the form of ax is equal to b. So we're going to go over here and rewrite this. In this case, our x is going to be our t1 and our t2s, because that's what we want to solve for. So we're going to set it up as t1, t2. Using this as our x, we can then write our A matrix. So this column is t1, and this column is t2. So we see that it would be root 2 over 2, negative root 2 over 2. And then our t1 in our second equation, again, is root 2 over 2. This time our t2 is positive, root 2 over 2. And we're just going to move this over to this side. So we only have anything that's multiplied by t1 or t2 in our matrix. So that means this t1 is t2. And since we moved our mg to the other side of the equal sign, for our first equation, it's still just equal to 0, but for our second equation, it is equal to mg. So from here, there's a couple different ways you can solve this. Your first option is to solve for x using inverses. So you can solve for the inverse of a and then multiply that by b, which in this case, this is our b. to then get our values for T1 and T2. You can also just RREF and then solve the system.